Yeah, the floor is yours.
Thank you. Can you see my slide?
Yes.
Yep.
Okay, cool. Thanks, everyone. I'm presenting our recent work on competitive programming. The title is Competition Level Code Generation with AlphaCode. So currently, the paper is still hosted on our DeepMind website. We have sent it to archive like a month ago, but it's still not yet on archive. I have no idea what's going on behind the scenes. So this is right now the only way to access our paper.
That's weird. I thought archive just accepted the papers.
No, there's a review process in archive. They have to review that the paper is on topic.
Oh, really?
I wouldn't expect that to take a month.
Yeah, unfortunately, the volunteer group for reviewing it does not scale at the same rate as the number of submissions.
Yeah. Anyways, so that's where we are right now. So the topic of the work is basically developing a system that can do competitive programming. This basically is an example of a competitive programming problem from the Codeforces platform that we use to gather training data and also do evaluation, just to give you a flavor of what these problems look like. You can see a big natural language description, and all of these are basically part of the problem description. There's a story, there's also some specifications about input and output. There typically are some example inputs and outputs as well. Sometimes there's also an explanation of what's going on. So for this particular problem, what it asks you to do, like after you as a human read this whole description and then parse what it is about, then you can see that it basically is a task of transforming strings. So here, each example has two strings. So the first number basically tells you how many test cases are there how many individual examples are there in this test case. So 4 means there are 4 test cases. And in each test case, there are 2 strings. One is a source string, the other is a target string. And what you are asked to do basically is that initially you're supposed to type in this string, A, B, A, B, A, for example. And if you just type those keys, then you get this string. But this problem gives you a twist such that you can replace some of the keys with a backspace. So what a backspace does is basically to delete the previous string, the previous character that you just entered. So in this case, you can go from this string to this string by first, instead of typing A, you type a backspace because your current string is empty, it does nothing. And then you type B, A, and B, then you get string B, A, B. And then you replace the last A with a backspace. That basically deletes the previous B, and that gives you BA. Okay, so this means that it is possible to find a sequence of keys, either normal keys or backspace, that transforms, goes from the source string to the target string. And therefore you output yes. And if you can't find such a sequence of backspaces mixed with normal keys, then you output no. So that's what this problem is about. So it's actually not a very trivial problem, and you have to really parse this natural language description very carefully to understand what it is about. So another thing about competitive programming problems is that by reading this description, you only know what the problem wants you to do. You don't know how to solve it. So you basically can verify that you see this example, you can verify that you can get yes or no, but that doesn't tell you what algorithm you should use to actually implement a system that tells you how to do that. So that's another more difficult part of this problem. By the way, if you have any questions during the talk, feel free to ask. I would very much prefer this to be more interactive. So this is a solution found by our system that actually correctly solves the problem. So you can see it is actually a complete program. So in this case, it's a Python, but our system can also generate C++ as well. So it is a complete program in the sense that it does read the input from the standard input in this case. it reads those strings. It actually have a fairly non-trivial algorithm that solves this task. What it does is it basically goes from the end of the string and goes backwards. And if they match, then you keep it. If they don't, then you use backspace. So it's kind of like a dynamic programming or greedy algorithm that you have to think a little bit to figure it out, basically. And at the end, after it did all the calculation, if it matches, then you output yes. If it doesn't, you output no. So it has both the reading the input data and does the computation and then creates the output. So it has this whole thing. And being a complete program means that we can actually execute it on test cases and then also observe its behavior and do all sorts of nice things with execution. And another thing to note is that this program is actually not a short program. So it definitely has quite a few lines and it has a complicated logic. So if you just try to search for it, then it will be very difficult. So we really need to have some model that can get to the right direction. And that is also a difficult part of this problem. Okay, any questions about problem setting so far?
Yeah,
go ahead.
Yeah, so maybe this is a question for much later in the talk, but I'll throw it out there now, and then maybe it's a topic for discussion at the end. But one of the things that I would be very curious to see is if this is the output of the system, right? If this is the algorithm that the system comes up with, what is the closest algorithm in the corpus? Like if you were to go and just scan the whole corpus and look for the piece of code in the corpus that is closest to this, how close would that piece of code be? Right. So I would expect that this exact thing is not probably not in the corpus, but how close is the closest thing in the corpus to this problem?
Yeah, it's a very good question. I do actually have a few slides on that, so I'll get to that later.
All right.
And the short answer is there is basically no very close programs in the training set. And we basically take a solution and then look into the full training set, including GitHub and also our fine-tuning training set, and try to find the maximum overlap. So we basically find some overlap in the logic about reading the data, because the data format can be very common across problems. But the key logic, we've never found the key logic to be copied from any of the training solutions. Okay, so let's move on. And this is basically what our model sees as input. So we format this whole description into a big text string, and a slight twist is that we put it into a big comment. I think in this case, there's some strange thing going on because the comment is C++ style, but the solution is Python style, which is a bit unexpected, probably is a mistake. But I do want to go to this AlphaCode website to just show you how this model works in practice. Let me see if I can switch to a new tab.
Oh, you're muted. Yeah, you got muted.
Sorry, yeah, I'm just not very used to Zoom. So I changed to this AlphaCode website. Can you see this website? Yes. Okay. Basically, yeah, this has some nice animations that tells you how our model is doing. Basically, this is a full problem description. You can see it is fairly long. And then this is the solution our model generates. So you can actually play it. You see that it actually generates the program token by token. And this website also contains some nice visualization of the transformer attention mechanism as well. So you can see that when it generates each token, which part of the program or the description it is looking at. And we also have the probability distribution for each token as well. Yeah, let me just stop it there, and then you can look at it yourself. Let me go back to the presentation. Okay, cool. Let me move on. So just a very quick, brief summary of our results. So we did an evaluation of our system on Codeforces. So it's a very popular platform that hosts regular programming contests. And they say they have like 500,000 active users. And we evaluated on 10 contests. So we, when we did the evaluation, we were pretty careful about not allow our model to cheat by just remembering the training set. So what we did was all of our training and validation data comes before all of these 10 contests in time. So that we train on data that appeared online basically after, before all of these 10 contests, so that our model that doesn't see any additional data compared to a human participant would see if they participate in those contests, basically. And in these 10 contests, our model ranked in the top 54.3% across those 10 contests. So you can see the ranking here. And over this 10 contests, our model also got an estimated Codeforces rating of 1,238. So this rating is basically like an ELO score that tells you how good you are compared to all the users. And if you look at this ELO score rating, then we're in the top 25%. So these two are a bit different because the distribution are a bit different. And we hypothesized that the better users tend to participate in more contests. So the contest rating will be slightly lower than the overall rating ranking, because that's among all the users on the platform. But these are among those users that actually participate in contests. But regardless, I think this shows that our system is at about a median human level performance if you look at this 54% ranking. And to just give you a more intuitive understanding of what that means. So this basically means that our model reliably solves the A and B level problems. So in each programming contest, there typically are like 6, 7 problems in a contest, and they're ranked from difficulty from the easiest, like A, B levels, and then all the way up. On Codeforces, you go up in the letters like C, D, E, and F. And our model can pretty reliably solve the A and B level problems. And those problems are typically quite simple. So there are some simple logic that you need to implement, but there are also sometimes a bit more difficult problems that involve some data structures and slightly more advanced algorithms as well. And for these problems that the model do solve, it solves them with, on average, 2.4 submissions per problem. So it's quite efficient at solving those problems. So in this setting, we restrict our models such that they can submit a maximum of 10 submissions per problem so that we are not overwhelming the platform. And that means we have to generate a bunch of candidates and then somehow narrow it down to just 10 submissions and then submit them. And the fact that we solve most problems with a very small number of submissions, in this case, average 2.4, that means many of those solutions to these problems are actually already quite good, even in the first try.
So this 2.4 solution, 2.4 submissions per problem. So that means that it's basically in the top 3.
Yes, but what we actually found was it got most of those problems that the model does solve. It gets it in the first try, and sometimes it takes like quite a few more tries, like 8, 7, and things like that. And then the average is like 2.4.
Wait, when you say first try, I mean, I guess I don't know like exactly what the structure of the algorithm is, but does this mean like presumably you have this these input output examples, and you're using those to prune the search?
Yes.
So you mean there's 2.4 programs that pass all the input output examples and get submitted? Or
So
is
the
it-
evaluation, yeah, the evaluation, I have to maybe explain it a little bit. Let me go back to this example. So here is an input output example in the problem description. These are always visible to all the contest participants, but the platform also has a set of hidden test cases that are not visible. So all we have access to are those that are visible to everyone. And we do use these to filter our solutions. But we don't have access to the hidden test cases that only the platform has. So we still need to submit to the platform to see whether our solution is correct or not.
Got it. And is the feedback from the platform just a yes or no?
Yes, it wouldn't tell you like where you failed, but it would tell you whether you're correct or not.
Okay, got it. Thanks.
So this is a big distinction to many other program synthesis work, like input-output example-based, because we don't have access to the full set of test cases that we need to satisfy. So it does require the model to do understand like the natural language what the task is about, rather than just directly find a program that satisfies all the constraints. Yeah, go ahead.
Oh, sorry, sorry, this is Josh Tenenbaum. I only joined late, I'm sorry. But I was just having trouble understanding that last example you showed where the, like with the ABBA, like is the 4 test cases, are those like input output examples? Is that what's going on? Or just so I understand. Like
yeah,
I
yeah.
see it says 4 examples and there's 8 lines of code, or there's eight lines underneath that. Is it like,
right? Yeah. Yeah. So here in this example, there are 4 test cases in this example, and each test case has 2 input lines. So basically, here an input is
okay.
ABA. This is the source string. BA is the target string, and you are asked to check whether it's possible to transform this into this. And if yes, you output yes. Otherwise, you output no.
I see. Okay, great. Thank you.
Sure. Okay, let me continue. So as I said, the model basically reliably solves the easiest problems in the contest, the A and B level problems. But it also managed to solve a few harder problems, including one rated at 1800. So this would be like a C or D level problem. And as I said, this setting basically restricts our models to only make 10 submissions to the competition platform maximum for each problem. But we also tried a more permissive setting where we allow the model to submit more, and we maxed it at like 500. So in this case, we see that the average ranking improved from 54% to 48.8%. So this is a small improvement if you allow the model to submit more. But in this case, you also see that the model would use more submissions to solve the problems. So that's it goes up from 2.4 submissions to 28.8 submissions per problem on average. Okay, so that's our result. And then before I go into my approach, let me basically explain why we want to do competitive programming or code generation. There are a few reasons. I think many of us in this meeting would also share our intuition as well, because we think programming is a great tool for problem solving, and programming problems are good benchmarks to develop problem solving models. In particular, in our case, for competitive programming, we have very clearly defined automatic correctness checking based on test cases that will give us very reliable metrics. And it can also drive research on a wide range of areas. And on the practical side, if we can develop models that can write code and understand code, then it would also help the developers or even non-developers to write code easier, or basically give them the capability to generate code even if they don't know how to code. So that would be a great vision for us as well. And our approach looks like this. So we do have a pre-training stage where we train our model on all the GitHub data such that it can learn good representations of code and also can generate good code. But generating good code is not even enough because our competitive programming problem has a very specific setup. So we did fine-tune the model on a data set of competitive programming problems and solutions. And after fine-tuning the model, we'll be able to generate solutions for some problems in a good style. But that is still not enough. If you generate just a small number of samples, you're not very likely to hit the correct one. So what we do at test time is basically for every problem, we will generate a large number of samples, like up to 1 million samples per problem from our model. And then, as I said, we restrict our number of submissions to just 10 per problem. So that means we would filter that 1 million samples down to just 10 good candidates. And for doing that, we did use filtering, like filtering based on the visible example test cases in the problem description. We use that to do the filtering. But we also have a few other things that we do to filter the test cases. Like we cluster the solutions based on their behavior. And based on the clustering, we can better choose those good candidates as well. So this is kind of a very high level overview of our approach. And this is kind of a progress of last year. We started at a very low solve rate on our data set, which is like around 5% or even lower than that. And we gradually improved that to 34% on our data set. So this is a solve rate if we allow the model to submit 10 submissions per problem. And if any of those 10 solves the problem, we say that problem is solved. So this 34% is the percentage of problems in our data set that the model is able to solve in that setting. And we evaluated this model on Codeforces that give us the top 54% number on the Codeforces competitions.
And I have a question.
Yeah.
So is the x-axis here like time?
Yes. This is a very rough diagram, so don't read it too much, but it's roughly time.
Like when was the first point? Was this like a year ago or something?
The first point was around March or April, I think.
Right.
Yeah, we were pretty low at that point.
I'm curious, the last point is scaling up, and what kind of model were you using before scaling up, and how important was it to, is this scaling up in number of parameters or the million samples kind of thing? And, you know, how good can you do without scaling up, / what does the small model look like?
I actually have this on the next slide, actually. So our model is basically an encoder-decoder transformer with some tweaks for efficient sampling. Because as I said, we need to basically generate a lot of samples. So we do need the architecture to be efficient to be able to support a generation of large number of samples. And to your question, this scaling up is mostly scaling up the model parameter size. So we went up from, I think at this range, we're about 1 billion parameters or 3 billion, but at this point, we're at 41 billion parameters scale. The 1 million samples happened around here. Initially, we were just using like 100 or 1,000 samples per problem. And then we realized that we can actually scale up the number of samples to get performance gains. So we tried that very early on. At this point, we're already at 1 million samples, but we kept the model size to still be relatively small to iterate. And towards the end, we scaled up the model size as well. So this is basically what our model, yeah. So this is basically what our model looks like. So we have encoder decoder. We did make some tweaks to support more efficient sampling with multi-query, single key value attention, and by using an encoder decoder that allows us to use asymmetric architectures on the side on these two sides. So we have a shallow decoder and a shallow encoder, a deeper decoder. So that also made it more efficient for sampling. These are the few models that we used. The small ones are close to 300 million parameters. So we used this for a long time. We stayed at 1 billion parameter for a long time, and then later on we scaled up all the way up to 41 billion parameters. But scaling up is very costly. So the 41 billion parameter model did take a lot of resources to train. So we used basically 1,000 TPUs, and we trained that for almost a month. And that actually didn't train the model fully. So this model is heavily undertrained still. So we believe that if we train it for even longer, it would be better. But even at DeepMind, sometimes you don't have enough resources to do.
If you ask, how much does that cost in dollars approximately? 1,000 TPUs for 4 weeks?
Like $5 million.
It is not very cheap, but we didn't really calculate this budget. But you can maybe look it up how these TPUs are priced.
Okay.
I have a question. When you have like billions of parameters, you typically also have billions of tokens in your data. Do we know like how big the data set was when you train it?
Yes. So like here we have this training setting that basically tells you how many tokens that.
Oh, there we go. Okay, thank you. Yeah, that's what.
Train each of those models, but I think I have the data sets statistics somewhere. I don't. So basically, our pre-training data set grabbed all of the GitHub that we can use for training these kind of models, and it is about 700 gigabytes of data.
I see.
Here you see the token numbers to be a bit more than that because we do go over more than one epoch for some of these models.
I see. So when you say undertrained, do you mean it hasn't even finished like one epoch yet? Have you like 10% down, or like what does that look like, I guess?
So when we say undertrained, it basically means that it hasn't reached the optimal point for this model size yet. And that might not be after just one epoch, it could be multiple epochs. So we basically see that if you train this small model, for example, you can see the loss going down very rapidly, and then it enters a very slow decrease. And in that regime, it still improves, but it's not optimal. It's not an optimal way of using your compute. You would be better off just going for a larger scale model.
I see.
So that's what we mean by optimal.
That's
so for the 41B model, we haven't even reached that point yet. So
I see. Thank you.
Okay, so this is the model, and then our training data set. We pre-train on GitHub. As I said, it's a big GitHub data set with 700 gigabytes of data, and we fine-tune on the competitive programming data set that we collected ourselves. And this is some statistics about our data set. So in the training set, we have about 13,000 problems. And for each problem, we have a few hundred solutions, both correct and incorrect, in 3 languages, C++, Python, and Java. And for each problem, we also have a bunch of test cases as well. So there are this so-called example test cases. These are the ones included in the problem description. And there are also hidden test cases that are held out by the platform, but you can still see some of them on the platform after the competition is finished. So that's where we scraped those hidden test cases. But the thing is, these hidden test cases are still not enough because there are some very long test cases that they don't even show on their platform. So this is basically the amount we can get by scraping them. And we also generated a bunch of test cases by basically randomly mutating the test cases we already have, and then pass those randomly generated test inputs to the correct solutions that we have, and then see what their outputs are. And by doing this, we can create a lot more generated test cases. So we found that these generated test cases are very important to reduce the false positive rate of our evaluation, because with just 10 test cases, it's very easy to have a solution that do pass all of them, but still don't solve the problem that you want, because the test coverage is very limited. And if we generate a bunch of more test cases, then that actually reduces our false positive rate by a lot.
So though on that note, I don't know if you're going to go more into that filtering step later, but I was wondering, I guess, are those extra ones you generate, they're not used to like condition the search of the original model, they're just used in the filtering step by clustering and then basically like, or
not
sorry.
really.
Uh-huh.
So these generated test cases are only used for evaluation.
Okay, yeah.
You can't use it to do filtering because the test generation process would rely on you having access to the correct solutions already. And that would be cheating if you use it for filtering.
Oh, wait, sorry. I thought that the generated ones were ones you did at evaluation time to augment your initial set of input outputs.
You use it to do evaluation, basically evaluating whether the generated sample is correct or not. But you can't use it to benefit the model to come up with a solution.
Right. Okay. Yeah. Okay. I think I got it.
Yeah, this is a subtle point, and I guess, but it is important for our problem setup.
I'm wondering, aren't like 165 test cases, like test problems, like a small amount?
It is small, yes. So this 100 is about 15 to 20 contests.
I see. So this testing is basically only from those competitions that you have not seen, that were not available before you scraped the data.
Yeah. I mean, we scrape all the data and then we made a temporal split, basically.
Right, I see.
Because our training set is so small, we basically want to use all of the available data for training as much as possible. And we use this small set of validation test sets. That does give us some variance in our results, but so far we found this to still be useful in driving research.
Right. And I'm wondering, I didn't fully understand what the solutions per problem here mean. Here, like 196, for example, in the bottom left. What does that number mean?
So this means for each problem, you have on average 196 C++ solutions in our data set from human users. Yeah, from human users.
All right.
And here it also says that 45% of them are correct and the rest are incorrect human solutions. So we have both of them. And by the way, this data set is already released on GitHub, so you can actually play with it yourself as well.
And does the model know if the solution is correct or not during training?
During training, yes, we give all the available information to the model.
Right. So we're going to talk about how you deal with the fact that there are this huge set of possible correct solutions for each problem.
A huge possible. Sorry, can you say that again? I didn't hear it clearly.
So during training, how do you deal with the fact that there are so many possible correct solutions? So do you score it as correct if it matches any of them, or?
So during, so our approach is basically a transformer model, encoder decoder. So we're basically just predicting the solutions conditional on descriptions. So it's a purely supervised training setup. So we basically use all the solutions and ask the model to basically predict all of them.
I see, but
each individual
given that for the same problem you have like 100 distinct solutions.
Yes.
If you give it the problem and it comes out with solution 10, or it comes up with solution 25, either one would just score as a perfect score, presumably, right? Or do you actually tell it, or do you actually have like a data point that says this description should produce solution 10, and then you have another data point that says this exact same problem should produce solution 25?
So all of those solutions will be treated equally in our training setup. And we use a likelihood objective for training. So it's not like reinforcement learning or whatever.
Sure.
Yeah. So basically, if problem A has 10 solutions, then we would have all of them will be treated as kind of independent examples that we give to the model. So the model would see a description to condition on, it would see a solution to predict, and all of them would be treated independently.
I see.
Like equally likely.
Yeah, so you'd have like A comma S1, and then A comma S2, and then A comma S3.
Yes. Yeah, but we do have a slight tweak in the fine-tuning stage where we have this kind of reinforcement learning objective called GOLD. So what that does is it has a reweighting of the solutions based on the model's likelihood. So the model would learn more from the solutions that it is already assigning a higher likelihood to.
I see.
So that would basically, if the model is not able to assign a good likelihood to some solutions, then it's fine to just ignore them.
Mm-hmm.
And we found that to be helpful by a little bit. Okay, I think I probably need to go a bit faster because we only have 20 minutes left.
Sure.
For evaluation, I think I've already talked about that. We allow a maximum of 10 submissions per problem, and it has to pass all the tests. So there's this important distinction between the example test in the description versus the hidden test that we don't see. And in terms of metrics, we report two metrics in the paper. One is 10 at K. So this means the solve rate with 10 submissions from a total of K samples per problem. And the other is pass at K. So this basically is the solve rate with K samples. And we submit all of them. So this will be equivalent to a perfect sample selection approach because you consider all the samples you have generated so far. And there will be a big gap between these two metrics that I'll show later. So some findings from our experiments. So the first thing we find that is one of probably the most important findings we have in this paper is that the solve rate actually scales with more samples. These two plots, this plot shows the 10 at K metric. This plot shows the pass at K metric. So the x-axis is the number of samples you generate per problem, and the y-axis is the solve rate. I'm plotting also different model sizes as well. So you can see that the solve rate basically scales log linearly with more samples, roughly, for both these metrics. And you also see there's a big gap between this pass at K metric and the 10 at K metric. For example, if you look at the 300 million parameter model, then it's a little bit below 20% mark on this plot, but it is a little bit below 30% mark in this plot. So this shows there's a big gap in terms of how we're choosing the 10 samples out of a million, for example. And right now we don't really have a very good way of choosing that. And this gap of 10% or even more for some other models, I think is a big potential direction that we can get more gains on.
Wait, sorry, how are you ranking them right now? Is it according to the, is there some log likelihood assigned by the transformer that you're using to rank?
So for this result here, the 10 at K result here, we basically generate whatever sample, whatever many sample we have, and then randomly pick 10 uniformly.
Doesn't the model give you a log likelihood of the generated sample that you can use?
It does, but it actually doesn't help us pick samples. We tried that.
Oh, really? I see. Okay.
Yeah. So yeah, there's also another thing that I forgot to mention. So when picking the samples, we do run all of them on the example test cases in the problem description to do a round of filtering. And after that, we randomly pick 10 uniformly. Okay, so this is this result. And then we also see that solve rate scales log linearly with more compute and with scales with model size as well. So here we see the solve rate scales with the training compute. Here we see the model, the solve rate scales with sampling compute as well. So one thing to note is that obviously the bigger the model, the slower it is to generate samples. But from this figure, you still see that even with the same compute, bigger models will eventually win out because of their better model quality. That we found to be quite interesting. This is a result for filtering. So this is just filtering with example tests in the problem description. And this alone can filter out 99% of our samples. Oops. So as you can see that this shows how many problems we can find at least one sample that passes the example test in the problem description. So this is just considering the example test in the problem description. And still, we can see that there are about 10% of problems. We can't even find a single solution that passed the example tests in the problem descriptions with 1 million samples. So this is an extremely difficult problem in itself, even. And we're asked to not only pass those tests, but also the hidden tests that we don't actually see. So that is an even more challenging problem. But this also shows that our models are actually not very good at generating correct samples. So we really need to sample a lot to find a correct solution. But on the other side, this means filtering with example tests is really effective for us. Another thing we tried was to pick samples by clustering. So after filtering, we can sometimes still get like thousands of samples that we need to narrow that down further to 10 submissions per problem. And choosing samples uniformly can be wasting your sample budget, because if you have 2 programs that actually have the same behavior, then it doesn't make sense to waste your 10 submission budget on those 2 essentially equivalent programs. And we came up with this clustering idea that by using a separate model that generates some test inputs. And then those generated test inputs will be used to run all the candidate programs. And then we look at what output those candidate programs will produce, and then group the programs together if they generate the same outputs on the same input. And by doing this clustering, we can then group a lot of semantically equivalent programs together. And then we can only just pick 1 program from each cluster, and that will be a better use of our submission budget. So this is the clustering that we found to be quite helpful. So this is the result that shows different ways of filtering, comparing no filtering at all. So you just sample 1 million, then randomly pick from them. Then you can see that that actually doesn't scale with more samples, because you're just generating 10 random samples essentially. And if you use filtering with example tests, then you can see that actually allows your model solve rate to scale with more samples. And if you then do clustering on top of that, you see the solve rate improve a little bit further. But still, there's a big gap from this point to this point, because this point is actually the kind of perfect sample selection. So we still see there's a big gap there. And for our biggest models, the 41B model with clustering on our validation set, it actually reaches the 34% solve rate that I reported earlier. So some other additional tweaks that we use to improve the sample diversity. One thing we found to be particularly useful is this metadata conditioning. In our data set, when we scrape the Codeforces platform and when we get all the data from all the additional data sources, we actually have some metadata. For each problem, we have some tags that basically tells us what type of algorithm to use. So here's an example. So text could be like binary search, or math, or dynamic programming, or greedy. So this is kind of a tag for each problem. And we also have a rating for the problem as well. So rating basically tells us how difficult it is. So here the rating is 3,100. So this means this is a very difficult problem. And then for solutions, we have some metadata as well. Notably, like whether the solution is correct or not, and what language the solution is. So during training, when we train the model, we can condition the model on all these kind of metadata that we have for the problems and for the solutions. So what we do is we basically format this into a string and then append it to the problem description, and the model would see them and then generate samples accordingly. These metadata are available at training time, but they're not available at test time. So what we do at test time is we basically randomize all of these. So we randomly generate a tag from the most popular ones. We randomly sample a rating in the possible range, and we randomize between Python and C++, but we stick to generating correct solutions rather than incorrect. And we found that this metadata conditioning can actually help improve solve rate as well, because we're really generating a lot of samples, and it's really important to get a lot of diversity in there so that we fully explore the search space of programs. And we found this to be an effective way of doing it. here are some more detailed results of all the ablations. So this part is an ablation of our data set from no pre-training at all. So that means just train our competitive programming data set. So that gives us some like pretty low solve rate. And if we pre-train on GitHub, then you can see the solve rate improves quite significantly. And this bottom table shows a bunch of fine-tuning tweaks that we used to improve our solve rate, starting from no tricks at all, and then adding master language modeling. So basically a BERT style loss that we use on the encoder, and some other stuff that I talked about, like tags and ratings. This is metadata conditioning. We also tried to add an additional loss to ask the model to predict whether the solution is correct or not, in addition to conditioning on them. And there's also gold that I talked about. It's an RL-like loss that basically asks the model to pay more attention to the things that it is already somewhat certain about. And then at the end, this is the clustering that I just talked about for filtering. So overall, if you combine all of those improvements at the 1 million sample scale, then you can see the solve rate improved by almost 10% from where we started from, all the way up to 28% on our validation set. I see there's a question in chat. Do you consider solutions that are functionally correct but slow? Good question. So in our data set, we actually do not consider that. So we just consider correctness. But we're aware that there are solutions that can be correct but very slow, because for competitive programming, this is actually important. If a problem asks you to come up with the n log n time algorithm, and you came up with a quadratic time algorithm, it would give you correct solutions, but it would just be too expensive to pass all the test cases. And if you submit that solutions to the platform, then it actually would not pass, even if they pass all the test cases on our data set. But this is a limitation of our data set because we don't have access to those really large test cases. They're not visible on the platform, so we don't have them. So that's why we cannot track them. But we did try to manually look at the solutions that our models find, and do find that we have a pretty high slow positive rate. So that means the solution is correct, but are slow. And we have about 46% slow positive rate. We reported that in the paper. So it is pretty high. But the false positive rate is pretty low. False positive means it's an incorrect solution that gives incorrect outputs, but are still treated as correct by your evaluation process. So we don't have much of that. So that is like below 10%, I think around 6% or 5%. But the slow positive thing is much harder to tackle. But we're kind of thinking about tackling that as well, but not in this paper. Okay. Let me move on. So we also compared with some other additional models that are published in the literature. Notably, Codex was published last year, and there's also this apps benchmark published last year as well. We compared our model with some of these other models reported on those data sets. So we compared we trained a 1 billion parameter model on this data, and then it already got pretty good solve rate on many of those categories. One thing to note is that apps doesn't contain as much information as our data set. For example, it doesn't contain those metadata, so we cannot really do that conditioning on this data set. And also it has, I think in terms of false positive rate, it doesn't have as good test coverage as our data set either. But basically the story here is that we tried it and it kind of matches the already published benchmarks, and we're happy. So we didn't really push it too hard. So this is this part. And then going back to the first question that Armando asked, we did analysis of the model's capabilities. In particular, we don't want the model to cheat by just copying solutions from the training set. And we found that the model basically cannot cheat and does not cheat by copying from the training set. So there are two things that we tried. One is to try solutions in the training set to solve problems in our validation or test sets. And that actually solves 0 problems if you do exact copy of the solutions. And another thing we tried was to basically look at the largest overlap from the model solutions with any of the solutions in the training set. So here's an example. This is a model-generated solution, and this is its closest neighbor in terms of the longest common subsequence. So you see that the overlap actually involves the code that reads the data. So in this case, is kind of like a graph format. So it's very common. So it's not surprising that this part has some overlap. But if you look at the core logic, so basically here the coloring tells you a decomposition of the solution in terms of longest common subsequences. So you find the longest common subsequence with the solution, and then you move it out, then you find the longest common subsequence of the remaining part with the training set, then you can see those coloring. And basically the core logic here doesn't really copy that much. And we haven't really found a single case where the core logic was copied from the training set. Some chats. When you do clustering of M samples, which also passes given IO, how many clusters do you have? So it's on the level of, I think it reduces the number of candidates we have by a factor of between 10 and 100. That's roughly what I remember.
Okay.
And also we found that the model actually also reacts properly to changes in the description and the metadata. That basically means that if you tweak the description in some ways, then the model reacts in a proper way. For example, if you change the description that asks you to find a maximum of something and you change it to minimum, then you can see that the solve rate decreases very dramatically. And another interesting thing is that we found that if we simplify the problem description, as you've seen from the example, it's a very long description. And if you just manually read it and then extract the key part of it and write it in a short few sentences, that actually improves the solve rate quite dramatically. So that tells us that the model still struggles a little bit sometimes to understand the natural language. And if you simplify that task, it actually helps the model. But there are also a few other things included in the paper as well that basically says the model reacts properly to changes. So it's not just trying everything, but rather actually paying attention to the description.
How significant is that first bullet? Just out of curiosity.
So we did a study of handpicked 5 or 6 problems, and the improvement was quite significant. So
I guess I'm wondering, I don't know if you guys can, but you could imagine trying to, like automatically do some simplification of the problem description. Is that something you've considered? If it is kind of very effective. I guess I don't know how much expertise is needed to do this, whether it's something easy to do or if it actually required significant amount of human effort to simplify the description.
I think the challenge is we don't really have a data set of simplified problem descriptions. If we have that data set, maybe we can train a model to do it.
Right.
Now, somewhat unrelated question. In the beginning, you mentioned this, really huge training time. How much of that was pre-training and how much of that was training on the task?
That, I think about 80% was pre-training and 20% was fine-tuning.
Thanks.
Sure. Yeah, maybe I can actually skip this part, but basically this says that validation loss, like likelihood, actually is not a very good proxy for solve rate. And we found that even though validation loss seems to have reached the minimum and started to overfit, but still you see solve rate actually goes up. So it's an interesting finding that we had. So I think we're right on time, and this is my last slide. So takeaways, this is, I think, the first time to reach a median human level performance in competitive programming with a code generation model. It's a really challenging task, but we've managed to reach this milestone. And our pipeline of pre-trained and fine-tune and then large-scale sampling and then filtering seems to be pretty effective for this task. We did tweak the architecture for efficient large-scale sampling, and some of our pre-training and fine-tuning tweaks does improve performance. And more importantly, our model does solve fully unseen new problems, and they do not copy from training sets, and they react properly to changes in problem description. So some simple things are verified again in this task, like pre-trained transformers are very good priors, and then fine-tune that on a small set of problems can actually create very amazing models. And scale does matter, both in terms of model size and sample budget. So that's it. I would be happy to stay for a little longer, but if you have to go, feel free.
Thank you. Thanks a lot.
I have a question, quick one.
Right.
So you showed early on this this visualization where the transformer was looking at the attending to parts of the text while it was generating tokens. Is there like a meaningful correspondence, like when it's generating some part of an algorithm, does it look at the corresponding part of the description in some meaningful way?
It's very hard to say. I personally don't find them to be that easy to recognize, to pick up the patterns, but I think if you look into it long enough, you might be able to convince yourself that there are some patterns. I didn't manage to convince myself.
Okay. Thanks.
But we do have quite a few examples on our website, so you can feel free to go look at them.
Mm-hmm. Cool, thanks.
I have a question. When you say at some point a small model began to like flatten out, it's time to switch to a big one, that seems like some kind of decision that you had to make. Do you like, is there some intuition on when to use it? Or like how is it? Yeah. Is it just by eyeball you see the curve, or like what is it? What does it actually entail, I guess?
So I think for us, it's a combination of training models of different sizes. And you do see that the performance, the loss curves or whatever metric you're tracking, there's a crossover point where the larger model starts to be better. So that's one. This is an empirical evidence. And the other thing is there are already some existing study about scaling loss for training large language models. There are quite some work. I think one piece of paper that we look a lot at is this paper from OpenAI that they have this neural scaling loss for neural language models. And they do a very detailed study of this kind of optimal compute trade-off and how to basically set your hyperparameters, how long you should train, and how that scales with both the compute and the dataset size and the model size as well. So that was a very helpful piece of research for us. Yeah, so it's a combination of both of these two.
Okay, cool. Thank you.
I think you mentioned that the metadata helped in the, how much of a difference did it make in terms of accuracy if you include metadata? I guess I'm generally interested in kind of, it seems like what you feed the model is really important. So if you can predict some of these auxiliary information, I'm wondering.
So the metadata part basically corresponds to these tags and ratings. So you can see compared to this previous one that doesn't have it, it does have a small improvement.
Oh, okay.
On the slightly larger sample budget.
I see. Okay.
This value thing, I think it also contains this value conditioning. So basically tells you whether the solution is correct or not. So that seems to have a slightly bigger improvement. Yeah, so it's not huge, but it seems to be useful. So we included them in our pipeline.
I see. So clustering is actually a pretty big, like the last line.
Yeah, that's right. That's right. I think this is because in this clustering step, we managed to run the programs and then look at this behavior rather than just relying on the model's prediction. Right. So that does bring in some additional information that we can use.
I guess it makes sense also, given that you're selecting among the programs that pass all the tests, right? All the all the visible tests, and so it makes sense that a lot of those programs would actually be equivalent, since at least on the small set of tests they're behaving identically, right?
Yes.
Right. Actually, that's a good, like, do you know how many clusters there are for a normal? Problem?
It can still be like hundreds of clusters for problems.
Right, but it's not
So-
like thousands or 10, million or 10.
yeah, I
Just-
think
so it's not
said
that
this
many.
earlier. Yeah, I think it reduces the number of samples to the number of clusters is typically like 1/10 or between 1/10 or 100th of the number of samples.
I'm wondering, have we tried predicting test cases?
Yes, we do that in this clustering stage because we do have to generate some new test inputs to do the clustering because all these programs already passed the example tests. So they behave the same on the example tests. So we have to introduce some new test inputs to run the
But
clustering.
you don't know the ground truth for these, right? You could imagine trying to predict the ground truth outputs from the problem description. I don't know.
That was my question.
Yeah.
That is very difficult.
But
I think if you can, sorry?
Have you tried?
But you don't actually need to predict, right? You only need to rank among, like if you have 100 clusters, you only need a model that kind of ranks the output of each cluster basically on a test case. So it's easier than like, oh, I actually want you to predict the exact output, but you know, right? Like it's just like 100 examples and you need to do some ranking.
Right. Basically ranking the clusters, right? Because each cluster gives you the same output.
Yeah. You can rank it by kind of this proxy of indirectly ranking the likelihood of a test case.
But yeah, so Kevin actually Kevin Ellis had a paper where they were looking at this idea of if you have the kind of situation where you have lots of inputs, but no outputs for many of them, you can still train a model that allows you to say, well, this looks like an output for this sort of problem versus no, this doesn't look like an output for this sort of problem. And I think in particular for things like text manipulation problems, a lot of times there's certain expectations about how the output of the text manipulation should look like. And so even if your data does not include the outputs, but for some of these problems, you have these outputs that look all truncated and weird, you can rank them lower than outputs that look a little bit more normal.
Yeah, I think that's a very sensible thing to do. We did try a little bit in terms of ranking the clusters. We tried some combination of likelihood and a few other things. We didn't manage to get a very good re-ranking model. So right now we still find that picking based on the cluster size is the best thing we can do. I think picking based on cluster size is basically, because cluster size is kind of the likelihood of a certain behavior, because all the samples in the cluster follow the same behavior. So I think that is also a sensible thing to do. We haven't managed to find anything that's better than that.
I see. Yeah, that's a lot of sense.
Yeah.
So I guess another idea sort of from the synthesis literature is, so we had the sketch of that paper a while back where in order to deal with this problem of how expensive it is to sample from a neural model, right? And especially, I mean, we're dealing with tiny models compared to these monster models that you're dealing with, but already it was expensive to sample. And so training the model to leave placeholders in the places where it wasn't as sure of what the output should be, so that then you could run a much more efficient search just over the space of completions for the placeholders. Essentially take advantage of the fact that if the model itself can see that, this particular token could be like 10 different things and it's not so sure which one it will be, it can just leave a placeholder, and then you can do, especially for things like searching for constants, it might be difficult for the model to figure out exactly what the right constant is, but you can run a really, really fast search over a huge space of constants, much faster than what it takes to sample over the model.
Yeah, I think that's a very very good intuition to have. I think we do recognize that if we don't ask the model to just generate the full sample in one pass, it might actually do better if you can generate some kind of sketch first and then try to fill in the holes. That is a very sensible thing to do. I think we didn't push that direction too hard, but it is definitely on the things that we wanted to try in the future.
How about predicting traces of programs? Have you thought in that direction?
We did, and we actually briefly tried it as well. So the thing we tried was we were thinking about having this program test output prediction as an auxiliary task for our model. So the setting is given the program and the test input, you predict the test output. And if the model is able to do that, then obviously the model has learned something about how the program runs. And on that task, I think we were getting accuracy like 70%-ish for some simple problems. And adding that as an auxiliary task to our training didn't really improve the overall solve rate. So we just briefly tried it and then discarded that idea. But I think if we push it further, then I'm sure that some version of it can still be useful because it just makes a lot of sense.
Right.
Cool. So I have to run, unfortunately, but this was awesome. Thanks a lot for the presentation.
Thank you.
Thank you
Yes,
for
so
having
it was great to
Thanks, that was
have you.
helpful. Thank you.
Thank you so much. This was really cool.
Yeah, thank you for the nice discussion.
All right, guys.
Bye.
See you next time.
See ya.
See you.